Right, let's look at general motion and using calculus. What we want to look at is how we can use differentiation and integration with respect to displacement, velocity and acceleration. And what you'll find is, if you've got displacement, you differentiate it, we get velocity. If you take velocity and you differentiate it, we get acceleration. That takes us down the staircase. If we then integrate, we go back up. So if I have acceleration, I integrate, we get velocity, and velocity integrate, you get displacement. This makes sense if we think about the definitions of velocity being the rate of change of displacement and acceleration being the rate of change of velocity. So this is this is what it might look like in terms of differentiating. We've got a function of t, displacement is a function of t, and we differentiate with respect to time, and that gives us velocity. And if we were to integrate velocity as a function of time, it gives us displacement. Let's now look at some examples of how this works. Right, in this example we're given a displacement, and we've got to work out the velocity and acceleration after 3 seconds. So let's have a look. Let's differentiate first, and that gives us 3t squared minus 10t plus 7. Now when t equals 3, if we substitute that value of t in, we get 4 meters per second for our velocity. To work out the acceleration, we simply differentiate our equation for velocity with respect to time, and that gives us 6t minus 10. When we substitute t equals 3 in, we get 8 meters per second squared. You might want to have a go at part B before we go over the solutions. Right, now let's look at part B. This time we want to find out t when we've got a value of v or 5. And so we can go back to our original equation, which we derived. So we've got 3t squared, take away 10t plus 7 equals 5. We can rearrange that and solve that quadratic. That gives us two values of t. It gives us 3.12 and also 0.214. So given it's a quadratic, there's actually 2 points during the motion where the velocity is 5. For part B, we want to work out the value of t when the acceleration is 6. Again, go back to our equation for acceleration, substitute 6, rearrange, and we end up with 2.67 at 3 significant figures. Okay, let's look at a situation where we have to integrate. We have a particle initially at rest at a point where s equals 3, and it has an acceleration at time t seconds given by a formula where a equals t cubed take away 2t squared. And we want to work out the velocity and position at time t. So we can start off by the fact that acceleration is the rate of change of velocity, so therefore if we integrate a, we get v. So we can integrate our expression of a with respect to time. We get t cubed minus 2t squared, and that gives us t to the power 4 minus 4 divided by 4 minus 2 t to the power 3 over 3 plus c. To find out c, we should go back and look at our original conditions, and we're told initially the particle is at rest. Therefore, when t equals 0, v equals 0. We can substitute those values in, and we can see that c will therefore be 0, and so we have an expression for v. Now to work out a, we can simply integrate v with respect to t, and to work out s, we can simply integrate v with respect to t, and that will give us t to the power 5 divided by 5 times 4, which is 20, minus 2t to the power 4 divided by 4 times 3, which is 12, plus k. Again, if we look at the original conditions initially, when t equals 0, we know s equals 3. So therefore, if we substitute those values in, k has to equal to 3. And we can therefore write an equation for s as follows. Right, let's now consider this example where a force acting on a particle of mass 5 kilograms is given by 20I plus 15T J. Let's just make sure we can see that T over there. And its initial velocity is 3I plus 25J. After 3 seconds, we need to find its position, given that the position, after 1 second is 8I plus 7J. We cannot obviously see, first we can obviously see there's some acceleration, velocity and displacement involved in this question. We can start by considering Newton's law, F equals ma, and substituting F, which is 20I and 15T, and that gives us m times a. And if we rearrange this expression, we can form an equation for a, and so therefore a is 4I plus 3t j. Now from acceleration we can then find velocity, and we'll therefore integrate acceleration, and we'll integrate each component separately. So we'll integrate the I part separately and the j part separately. You can think of it almost as two different integrals, and therefore they'll each have a constant which we'll call c and d. Now we're told initially the velocity is 3I plus 25j. We can therefore substitute t equals 0 into our expressions and derive some value for c and d. Turns out c, when you put t equals 0 in, and 4t plus c equals 3, it gives us c equals 3, and similarly d equals 25. Next we can now integrate our expression for v, and work out what s the displacement is going to be. Again, we'll integrate each component separately and give it a constant which we'll call e and f. Now that we've got the displacement, we're told its position after 1 second is 8I plus 7j. Okay, if I just speed that up, right, so we've got, once we integrate v, this is our new expression, and we're told that obviously after 1 second we've got 8I plus 7j. We can use those values to work out e and f. If we treat each component separately, we get e equals 3, and in fact f equals minus 18.5. And we're asked to find the position after 3 seconds. So if we write an expression for s and substitute t equals 3, then we have an equation for s after 3 seconds as 3I plus 70j.